So let's go ahead and get started. So let's start a new unit. We're gonna start chapter 8. So chapter 8 is one of the major reasons that people do statistics in the first place. It's called hypothesis testing. So recall that on the first day of class, we talked about the motivation for the class. And in general terms, we said that the motivation was there's some population that we wanted all the data for, but it was infeasible to get all the data for your particular population. So instead, we have to resort to a sample, a much smaller subset of that population. And from that sample, we want to draw a conclusion about that original population we were interested in. So far, we've seen an example of that process where we end up making a conclusion about the whole population using a sample. So the example we talked about was in the form of confidence intervals. So recall that in a confidence interval, we want to know some true number about the population using the sample. So an example of that kind of number is like the percentage of people who approve the president, or an average IQ, or an average weight, or a standard deviation. So those are examples of types of numbers that we want to know for the whole population using a sample. And the conclusion was in the form of a confidence interval. But that was pretty limited, because that type of conclusion that we were able to make is just a single number in the end. So today we'll talk about being able to make a much more generalized conclusion. And that conclusion is called a hypothesis test. So put into context, we're able to answer much more broad questions. So for example, instead of just wanting to know a number about the population, let's say you wanted to know whether a drug was considered effective to doing what it claims, like lowering cholesterol. So if you didn't have statistics, one way that you could do it is you could give the drug to every single person in the country and see what happens. So what's the issue of doing that?
It's not feasible.
Yeah, so one is not feasible, just like asking every person whether they approve the president isn't feasible. What's another reason?
Safety issues.
Yeah, safety issues, like people could die because you don't know the effects of the drug beforehand. And people dying is bad for business. So instead, oh, you can say that.
One could say that, yeah.
Oh yeah, one could say that, yes. So you don't want to just do this experiment for the entire population without knowing beforehand all the consequences. So instead, we're going to give the drug to a sample of people and then see what happens and then make a conclusion about the whole population. So now we're able to answer much more broad questions as to whether this drug works, as opposed to just getting a single number in the form of a confidence interval like before. Okay, so let's put this into context with a very simple example, but that example was able to generalize what all hypothesis tests end up doing. So let's say that you're walking down the street and you see a coin on the ground and you pick it up. And in your hand you notice that it seems to be weighted heavier on one side than the other. So you suspect that this coin is possibly unfair. So we always start with a claim. So a claim or an idea or a hypothesis, all the same thing. But usually it's called the claim. And in this case, the claim is that the coin is unfair. So when we say that the coin is unfair, what we mean is that it's unfair in the long run. It's unfair in the context of the population of all possible coin flips. So for example, if you were to be able to flip the coin a number of times that approaches infinity, like 1 billion times or even more, like 1 trillion times, then if the coin is unfair, then that means that you would not get exactly 50% heads for that coin flip in the long run if the coin was unfair. But if the coin is unfair and you flip it a very small number of times, like 10 times, then you very well could see variation even if the coin was perfectly fair in the long run. So if the coin is fair in the long run, after 1 million flips, and you flip the coin only 10 times, and you observe 6 heads, could that still be possible for a fair coin?
Yes.
Yeah, sure. So when we say the coin is unfair, that means it's not exactly 50% heads in the long run. In the short run, even if the coin were fair, it could still result in a number of heads that's not 50%. Okay. So what this claim has to do with is it's a statement about the population of coin flips. So this claim has to do with the population. So when we say the coin is unfair, it's unfair in the population of all possible coin flips. So in real life, if you had this idea that possibly the coin was unfair in the long run, how do you think you'd go about to make a conclusion about whether this claim is true or not?
Give it a test with a large enough sample to see what side it's going to fall on.
Yeah, so a surefire way is to actually flip it a number of times that actually approaches infinity, like 1 billion times, like 1 trillion times, and then see if you're getting 50% heads or not. If you're not getting 50% heads, then it's not unfair. But the issue is that we don't have the time and patience to flip this coin a number of times that approaches infinity. We don't have the luxury of looking at the population of coin flips. We can only resort to a sample. So just like the generalized issue that we've been talking about. So let's say that we already said that 10 coin flips was not enough, but let's say that we do 100 coin flips. So we're going to call this the observation. So we're going to observe after flipping the coin 100 times. Let's say that we observe 55 heads. So 55 heads turns out to not be exactly 50% heads, it's 55% heads. So 55 out of the 100. But because 55% isn't exactly equal to 50% heads, can you conclude that this coin is not fair?
No.
No, good. Because it still seems like it's close to 50% heads, and also you have to take into account that you're now flipping it a number of times at first infinity. So, in real life, what would your conclusion be?
Indeterminate.
Well, that's true, but we also want to phrase it in terms of, so let's say that we have a spectrum of where we could stand in terms of our position. So heads, fair coin is here, unfair is here in terms of our position on where the coin is. So when we say indeterminate, it's really a whole spectrum of here. But if you say indeterminate to someone, they might assume that it's exactly in the middle, where it could be an equal chance of fair or unfair. But when you say indeterminate, are you leaning more one way than the other?
You're leaning one way more than the other.
Which way? possibly towards fair, because you see that maybe this is close enough to 50 heads where you could say it's possibly fair. Okay, good. So the point is that yes, it's indeterminate, but maybe you're leaning more towards fair. So maybe your conclusion could be that the coin is maybe fair. But let's say that you have a second coin. Let's do case 2. And you wonder the same thing about the second coin. And you also flip it 100 times. And this time you observe 90 heads from 100 flips. So this second coin, what do you think you can conclude about whether the coin's fair in the long run?
That is not fair. Well, depending on what you're using for your confidence level, based on your numbers there, you're gonna say with this confidence level, this coin is, biased for heads, result from however many flips. So you're basically saying, yes, based on this information from these observation of 100 flips, you're very likely to get this, and then put your interval down. So
But in this case, would you lean towards fair or unfair?
it's definitely unfair.
Unfair, okay, good. So in both conclusions, you have some doubt in both conclusions, and you stated that with, basically involving a confidence level and so forth, so that's right. But, so both these conclusions have some doubt in them, but which one has less doubt? Which one are you more sure about?
The first, second.
Yeah, the second one, right? Because when you said that the second coin is unfair, you're much more confident that that's the case, that the coin is actually unfair. So all hypothesis tests have this structure. So let's summarize what the structure is. All hypothesis tests have a claim or an idea about the whole population. And in this case, the claim is that all population of coin flips for this coin will result in a percentage that's less than 50%, i.e. the coin is unfair. Will result in a percentage of heads that is not 50%, so i.e. the coin is unfair. And in order to test this claim, so we always have a claim. So in order to test the claim, we have an observation that involves one or more samples. In this case, we flip the coin 100 times, so we have a sample of 100 coin flips. So here we have a sample. And in that sample, we happen to observe this observation of 55 heads. So what we end up doing is working subconsciously, how we're reaching this conclusion of maybe the coin is fair, is we're taking this observation and subconsciously in the back of our minds, we're comparing it to some model. And the model in this case is that if the coin were fair, then we should be able to observe with the greatest likelihood how many heads out of 100 flips if the coin were fair. 50. So the model here is of a fair coin. We're observing 50 heads. So subconsciously what we're doing is we're comparing this observation, 55 heads, to the model of 50 heads. And if that comparison is close enough, so we compare these two and we say that they're close. And if the observation is close to the model, then we say that maybe the model could have generated this observation. And we say that maybe the model is true. So in this case, that's what's happening. We're saying maybe the coin is fair, or maybe the model of the fair coin is true. Any questions so far? So in the second case, really we're doing the same thing. We're taking this observation of 90 heads, And then again, we're comparing it to the model. Versus 50. And in this case, subconsciously we've determined that the observation of 90 heads is not close enough to the model of 50. And because it's not close enough, then the model cannot possibly be true. So our conclusion here is that because these are far apart, that the model cannot possibly be true, and the model of a fair coin in this case can't be true, so therefore the coin must be unfair. So again, in all hypothesis tests, we start with the claim for a population. We have an observation in the form of one or more samples. We take that observation, we compare it to some model. In this case, it's the model of a fair coin. And if it's close enough, then we reach one set of conclusions. Maybe the model is true. If the observation is too far away from the model, we reach another set of conclusions and say the model cannot possibly be true. So in a nutshell, that's all hypothesis tests have this structure. So at this point, you might be wondering, so also, every hypothesis test either has the first conclusion, maybe the model is true, or the second conclusion, which is the model is not true, the model is false. So all hypothesis tests, in the end, you're going to reach one of these two conclusions. Either maybe the model is true, or the model is false. So the one you end up using is based on whether the observation is close to the model or whether the observation is too far apart from the model. In which case you would be in one of these two camps. So the question is, now, how do you know whether the observation is considered close enough to the model or not? In which case, you reach the first set of conclusions. Or if it's too far away from the model, you would reach the second set of conclusions. So how do you draw that line between close enough and too far away?
Wouldn't that be based on your confidence level?
Yeah, so very good. So it turns out that that's where the statistics comes in, and we quantify whether the observation is considered close enough or whether it's too far away. So this step of deciding whether the observation is close to the model or whether it's too far away from the model, that's where the statistics will come in, and we'll talk about that. We'll quantify that together. But in a nutshell, you have a claim about the whole population, you use an observation in the form of one or more samples to test the claim. You take the observation, compare it to some model. If it's close enough, then you reach one set of conclusions that maybe the model is true. Vice versa, if the observation is considered too far away from the model, then you reach another set of conclusions and conclude that the model is false. That's the general structure for all hypothesis tests. Any questions so far? Okay, so we just did hypothesis tests for this simple example of whether a coin is fair, but we did it very intuitively, hand-wavingly. So now what we're going to do is formally. So we'll do the formal steps for hypothesis testing on the same example. So this will be categorized under hypothesis testing formal steps. So the first formal step to hypothesis testing is you want to identify two statements. So the two statements that you want to identify are the null hypothesis, and the second statement is called the alternative hypothesis. So the null hypothesis is abbreviated as capital H with a right subscript of 0. Or it can be abbreviated as capital H with a right subscript of O. So one is a 0, one is an O. But either one denotes the same idea, null hypothesis. And we'll talk about what that means in a little bit, but right now we'll just talk about the mathematical symbols. So for the alternative hypothesis, it's abbreviated as capital H with a right subscript of 1. So 1 as opposed to 0. And then also, the alternative hypothesis could be capital H with a right subscript of A. So either H1 or HA. And the null hypothesis is H0 or HO. Okay, so let's use the same example that we've used before, whether the coin is fair or not. And we're gonna start with a claim. So that's the statement that you start out with, or what's given to you. So we can always generate a statement that is the opposite to this. And specifically, that means whatever is left over from the original claim. So what's the opposite statement to the coin is unfair?
The coin is fair.
Yeah, the coin is fair. And now we have two statements. One of the statements will be the null hypothesis, the other will be the alternative hypothesis. We don't know which is which yet. So the next step, we're going to convert each of these statements into mathematical statements. So, and let's give this statement that we just called the opposite, let's give it a name. So we can call that the counterclaim. So let's convert each of these statements into mathematical notation. We're going to arbitrarily pick the bottom statement first. It doesn't matter which one you start with. But let's use this mathematical symbol P. So in the past, P represented the proportion of success for the whole population. In this case, the whole population of coin flips. So if the coin is really fair, then what should the value of P be? The proportion of success or heads for a fair coin. Yeah, it should be 0.5. So if the counterclaim is true and the coin is fair, then P should equal 0.5. What about if the coin is unfair? What should the value of P, the true proportion of heads for all population of coin flips, be?
You don't have that data yet.
Very good, we actually don't have it yet. But you can imagine if we were to flip it a number of times that approaches infinity, what would lead us to conclude that the coin was fair?
That P does not equal 0.5.
Okay, good. So we look at the proportion of heads after we flip the coin a billion times, and if the proportion of heads it does not equal 0.5, then that means the coin is unfair. So it can be anything as long as it's not 0.5.
I don't need to get too much into specifics about it, but wouldn't you want it to always be a certain distance from 0.5 to be confident whether it's fair or unfair?
Okay, very good point. So it turns out that when we say that the sample size and number of coin slips approaches infinity, that's important because the closer you are to approach infinity, the closer this will keep getting to the 0.5. So if that's true, then that's what this means. So the closer your sample size is to infinity, then the closer this p will end up being to 0.5. For example, if you flip the coin 1,000,000 times, you might observe 0.49998 heads. This is after 1,000,000 flips. But if you increase this to 10 million, for example, it needs to get even closer to 0.5. For example, there. So if this is true, then this statement is true, and that p is equal to 0.5. And so when we say equals, we really mean converges to. Gets closer and closer to. Any questions? Okay, so if the coin is unfair, that means that in the long run, p can be any number as long as it's not 0.5. So another way to say that is that p could either be greater than 0.5 or p is less than 0.5. Okay, so now we've converted each of these statements of the claim and the counterclaim into mathematical statements. So now we're ready to identify which one is the null hypothesis and which one's the alternative hypothesis. So you look at a statement that contains equality with the equal sign. And so in this case, the one that has the equal sign is p equals 0.5. So the one that has the equal sign, we call the null hypothesis. So in this case, that's HO. And the other statement remaining will be the alternative hypothesis, H1. So here, the null hypothesis HO is a counterclaim, which in English is that the coin is fair. So that's step one. We've identified these two statements, HO and H1. So again, HO will be the coin is fair, mathematically will be p equals 0.5. And the alternative hypothesis is the coin is unfair, where p does not equal 0.5. So the next step, step 2 in hypothesis testing, is we want to assume that the null hypothesis HO is true. So the thing that we're assuming true in this case is what statement in words?
We're assuming the coin is fair.
Yeah. So HO here is that the coin is fair. So in this example, we're assuming that the coin is fair. And mathematically, that means that P really does equal 0.5. So if you look at intuitively, what we were doing before is later on, we're going to take the observation of 55 heads, and we're going to compare it with some model. And if it's close enough, then we say maybe the model is true. And if they're far away, then we say the model couldn't possibly be true. But now you're starting to see that this model that we've been talking about generically is in the case of hypothesis testing, we look at the null hypothesis. So the model specifically is actually the null hypothesis. Because before the model was that the coin is fair, but that's what the null hypothesis is. So now we know that the model is really the null hypothesis. Okay, so in this case, we're going to assume that the coin is fair and that the null hypothesis is true. So within this step 2, we're going to visualize this with a distribution, our favorite. So the x-axis will have some variable of interest, and the y-axis will be a probability that that variable could take on each of its values. So because our claim here, our idea, has to do with a proportion of success, P, a proportion is really a number of successes out of another number of trials. So that's the variable that will be in our x-axis here. So a number of successes out of another number of trials. And because in our observation we end up flipping the coin 100 times, the second number will be 100. So we're looking at the number of successes or heads that we end up flipping out of 100 flips. So going back to, so the context here is that we have this visualization of step 2, which is we assume the coin is fair, and hence assume that the null hypothesis is true. So if the coin is really fair, and you flip it 100 times, then how many heads should you expect to observe with the greatest likelihood? 50? Yeah, 50. So at 50, we have a vertical bar with a certain height that corresponds to the probability of observing that number of heads. So of course, if you have a perfectly fair coin, like we're assuming, and you flip it 100 times, should you expect to observe 50 heads every time for that fair coin? No, because it's only 100 flips, so you're going to get variation. You very well can see 51 heads if you flip a coin, if you flip a fair coin 100 times. But the likelihood for that is going to be a little bit less, and so hence the probability will be a little bit less than for 50 heads out of 100. So as you move away from 50 heads for a fair coin, the probability will get less and less that you actually observe that number of heads out of 100 flips. So the same thing the other direction. So this is what the distribution looks like if the coin is really fair and you flip it 100 times. This is what the probability distribution would look like for each of the number of heads that you end up observing. You see the most probability or representation at 50, and as you move away from 50 heads for a fair coin, you see less and less likelihood. Any questions? Okay, so with any conclusion that we make in statistics, it'll come with a certain degree of confidence in that conclusion. So that's going to be given to you. So in this case, let's say that it's given that the confidence level is 95%. Let's go ahead and visualize that in the distribution too. So the 95% confidence level means that how much is left over from 100%? Yeah, 5%. So this 5% left over, you might have seen it previously in your homework, that's called alpha, or also the significance level. So alpha is always what's left from 100% for your confidence level. So this 5%, so let me go ahead and draw this.
5% is gonna be 2.5. Just wanna know if we're using a T or chi.
Okay, so we'll get there. So you have this distribution. The 95% corresponds to the body of the distribution. And then what's left over, the 5%, is in the tails of the distribution. So these two red tails have to add up to what's left over of the 5%. So it turns out that for a hypothesis test, sometimes you can have two tails, like we've drawn here, and sometimes you can have one tail. It's actually really easy to determine which one. We'll talk about that in a second. But the point is the amount of alpha, the 5%, is divided across all the tails. If you have two tails, it's divided across both tails evenly. If you only have one tail, then that full 5% is on one tail. So another question is, how do you know whether our picture here, the distribution, should involve one tails or two tails? So it's actually really easy. The way you find out is, remember in step 1, we identified HO and H1. So always look at H1 to determine the number of tails. So in this case, H1 is this statement, which is P does not equal 0.5, or P is greater than 0.5, P is less than 0.5. So you look at the number of inequalities. So there's actually two inequalities here. P is greater than 0.5 or P is less than 0.5. So the number of inequalities tells you the number of tails. So in this case, you have two inequalities, so you have two tails. So two tails means there's one on the left and one on the right. If you had a situation where H1, for example, was P is only less than 0.5, and there's no or P is greater than 0.5, then this would be a one-tail test. And not only is it one tail, you can tell whether it's on the left or the right side by looking at this variable P being less than the number. So less than is left on the number line. You can also draw a little arrow here to the left. So that tells you that this less than is a left tail test, in which case you would draw only a left tail, and the full amount of alpha would be on that one tail, if it was a left tail. So again, you can tell the number of tails involved by looking at H1 and looking at the number of inequalities. And alpha will always be distributed across all the tails evenly. If it's two tails, then each tail will be alpha over 2. If there's only one tail, then the full amount of alpha will be on that tail. Any questions? Okay, so in this case, confidence level is 95%, alpha is 5%. We have a two-tail test because H1 has two inequalities, so therefore alpha, the 5%, will be distributed across both tails. So these two tails will add up to 5%, so therefore each tail individually is how much?
Without trying to square it, it's gonna be 0.025.
Yeah, 2.5%, which as a decimal is 0.025. So this is the visualization of this step 2 assumption, which is you assume that HO is true. In this case, you're assuming that the coin is fair. Any questions so far? Okay, so let's go to step 3. So basically, I'm just gonna leave the two conclusions up and erase all the code. Okay, so step 3 here is we're gonna ask ourselves, is the observation consistent with the idea that HO is true? So basically we have an observation or a data point, and we want to know whether it's consistent with the distribution representing the idea that HO is true. So in the past, how would we determine whether a single observation was consistent with the underlying distribution?
The graph would be symmetrical.
Yeah, so basically, it boils down to, we have a distribution that has a body and one or more tails, and if the observation is inside the body of the distribution, then we say it's consistent with that distribution. If it's in one of the tails, that means it's too extreme, it's either too high or too low, which means it's not consistent with the distribution. So, to answer this question, it basically just boils down to, is the observation in the body or the tail of the distribution? So, let's say that our observation had been 55 heads. Now this is the first time we're incorporating the observation in. So let's say 55 is here. And right now I'm drawing it in the body, but I'm just guessing. So later, if we actually determine that the observation to be on the tail, we'll redraw it. But for now, let's just guess and draw it in the body of the distribution. So how do we know for sure whether to draw the observation 55 heads in the body or the tail?
Depends on how the question is asked. If it's asking for what are the odds of this particular one for this thing, it's going to be in the body. If it's asking what the outlier is, like a H with a subset, so you're thinking one into the other, or the space in between. Again, it depends on how it's particularly phrased, but it tells you, I want the percentage of what you think of for this, where H0 is true, we're saying it based on the observation is equal to either 55% for maybe or 90% for not at all.
Okay, so remember this distribution has very well-defined tails. So the tail on the right has an exact area of 0.025. Tail on the left has that exact area. So we know where the tails actually start and how much areas the tails must have. So this boundary of where the tail starts, we call the critical statistic. In this case, the underlying distribution is a bell curve because we're dealing with a variable that is a number of successes out of another number of trials. So each of the probabilities of a number of successes out of another number of trials is a binomial probability. So this whole distribution is actually a binomial distribution. And you see that the general shape is a bell curve, so we can approximate most binomial distributions with a bell curve. So this ends up being a bell curve. So because it's a bell curve, this line where each of the tails starts can be denoted with a z-score. So we have a critical z-score here. So there's a z-critical where the right tail starts, and a z-critical where the left tail starts. So how would we be able to find those critical values? Let's start on the right. How would we be able to find where this z-score starts that starts the right tail?
You already have the number, so, I mean, what your number is for 100 flips based on that observation, so plug it in with what you've got on your Z, so, you know that both ends added up is 2.5%, so everything left of that end should be 95.
Okay, good. So recall that we have a z-score chart that gives us a relationship between two quantities, a z-score and the area to the left of the z-score under the bell curve. So if you know one, you can find the other. In this case, we're trying to find the z-score. So we're trying to find this z-score, so we knew the left area, we'd be able to find it using the chart. So in this case, just by looking at this, we immediately have a right area under the bell curve, but not necessarily a left area. So how would we find the area to the left of this z-score we're trying to find?
Subtract from R,
Subtract
1 from 1.
Yeah, okay. So 1 minus the 0.025 will give us the total left area. Or you could have added up this middle area of 95 plus the left tail of 2.5. You'll get the same answer, it's 97.5%. So this left area, relative to this boundary of where the right tail starts, is 0.975. So look up 0.975 as the left area, and you'll get the corresponding z-score. And the answer should be 1.96. So z critical, or where that line that starts the right tail, needs to be 1.96. So the other tail, the left tail, also has a critical z-score. And because the bell curve is symmetric, what do you think it will be?
Negative 1.96?
Yeah, it'll be the same value, because starting at the mean, it's the same number of standard deviations to get the same amount of area in that tail. So it'll also be 1.96, but it'll be negative since it's going the other direction. If you didn't have that insight, that's fine. You just look up a left area of 0.025. And in the chart, you'll get negative 1.96. So now we have these exact values for where these two tails actually start. But our observation is 55 heads. So how do we know for sure whether it crosses any one of these two tails? So our observation of 55 heads. How do we know it crosses either tail?
You would look that up on the z-score chart, and if it's greater than 1.96, greater than or equal to 1.96, or less than.
Okay, you're on the right track, because we have the z-scores for where each tail starts, so all we would need to do is convert our 55 heads to a z-score. But how would we do that? Would we use the z-score chart to do that? Because remember, the z-score chart requires us knowing the left area to get that z-score.
Right.
No, this would be, so P is your probability and your number is 100, so P divided by, P multiplied by 100, so you get your mean. So, yeah, P divided by 100 would give me my area in between.
So remember, you can either find z-score with the chart if you know the left area. Then you can use the chart to get the z-score. But in this case, this observation of 55 heads, you don't necessarily know what that left area is. So we wouldn't be able to use the chart directly to get the z-score for the observation. But there's another way in the past that we've been able to get z-score, is the z-score formula. Right, so the z-score formula.
X minus mean over standard deviation.
Okay, excellent. So z-score formula is nothing more than what it means to be a z-score of a data point, which is the number of standard deviations that data point is away from the mean. So the data point is x, so you subtract the mean, divide by number of units and one standard deviation. So the issue is, in some problems, you're given the mean and standard deviation directly. But in this case, you notice that you're not given the mean and standard deviation directly, and maybe somehow we're able to find it easily. So is there a way for us to find the mean and standard deviation in this case?
We have the number of trials, which is 100 flips. We have a probability of 0.5. That n times p. That's-
Okay, excellent. So recall that because the claim in this hypothesis test has to do with a p, which is a proportion of success, you can also say that a proportion of success is a number of successes out of another number of trials. And that's what our x variable involves here. And so each x variable is a number of successes out of 100 flips. So each y variable represents the probability of that. So the height of each of these bars is the probability of a number of successes out of another number of trials. That's a binomial probability. So all of these probabilities, or heights of bars, are binomial probabilities. So this whole distribution is a binomial probability distribution, in which case we said that there was a simple shortcut to find the mean and standard deviation. So the mean is mean is n times p. Standard deviation will be square root of np cubed. So in this case, what's n and what's p?
P is 0.5, N is 100.
Yeah. So, so one tricky thing, recall that p is the proportion of heads in the entire population of coin flips. Not the sample of coin flips, the population of all possible coin flips. So here, in the sample of 100 coin flips, you have 55%. But that's not what this p is asking. This p is, for the population of coin flips, what's the proportion of heads? So we don't actually know that, but there's this second step in hypothesis testing, step 2, where we assume that HO is true. And we assume that p equals 0.5. So here, this p, we're going to assume that that's 0.5. So we're using n is 100 flips, and p is 0.5. So the mean is going to be 50. And that's consistent with our intuition here, which is if the coin is actually fair and we flip it 100 times, the most likely number of heads is 50. So that's the mean, which is 100 times 0.5, which is n times p. And then we'll do the same on the bottom here. Standard deviation is the square root of npq. So n again is going to be 100. P will be 0.5. If p is 0.5, then what's q?
0.5.
Also 0.5 because q is 1 minus p. So we're going to do the square root of the quantity, 100 times 0.5 times 0.5. If you bunch that in, you'll see that you'll get 5. Because it'll be the square root of 25. Okay, so now we know that the mean of this distribution ends up being 50, and the standard deviation is 5. So going back to our z-score formula, we're going to use x, which is 55, and subtract the mean of 50 divided by the standard deviation of 5. Okay. So recall that when we did this before, earlier on, this was actually a binomial distribution with all the gaps in it, which we approximated with a bell curve. So in the past, when we did this, anytime we calculated the z-score, we used continuity correction. Recall that at 55, we added and subtracted one in either direction, and really, when we did it that time, it was supposed to be from 54.5 to 55.5. So when we did it properly last time, the z-score that we used should be 54.5. So that's how you do it properly. But in this section, we're going to approximate and basically not worry about continuity correction. And you'll see that your book basically forgets about continuity correction. But I mentioned that just so you know that it's the same thing that we've talked about before, but in this case, we're just choosing to ignore that one step of continuity correction. So in this case, it'll be 55 minus 50, which is 5 divided by 5. That's going to give us a z-score of 1. So that means that the z-score of our observation, we call that z-test. So z-test will be 1.0. So at 55 heads, that has a z-test of 1. So now our observation has its own z-score called z-test. The dividing line where each tail starts has its own z-score called z-critical in red. So to decide whether the observation is in the body or the tail, we compare z-test to z-critical. So let's first determine whether the observation is inside the right tail. So the right tail is everything to the right of where the right tail starts, which is 1.96. So our z-score, z-test, is only 1, so that means it's to the left of 1.96. So that means it can't be in the right tail. What about whether it's in the left tail? Could it possibly be in the left tail?
No.
Yeah, so you can use the same reasoning. Everything to the left of negative 1.96 has to be in the left tail, but our z-score of 1 is to the right of negative 1.96, so it can't be in the left tail. Another way that you could reason it is that you know that this, where the mean is, the peak here has a z-score of what? So at 50, where the peak is here.
0.
Yeah, this z-score has to be 0. So our z-score is 1, which is to the right of the mean, which means it has to be to the right of the left tail. So it can't possibly be in the left tail either. So that means that because our observation, having a z-test of 1, is not in the left tail, and it's not in the right tail, so therefore it must be in the body of the distribution. Any questions? So we determine whether the observation is in the body or the tail of the distribution simply by comparing z-score to z-score. Find z-critical using a chart, and find z-test using a formula. Any questions? Okay, so now that we've concluded that the observation is in the body of the distribution, now we're ready to make a conclusion. So recall that this is in the context of answering this question, which is the observation consistent with this idea that HO is true? And you can only answer that question one of two ways, yes or no. So if the observation is in the body, then the answer to that question is yes, the observation is consistent with the idea that HO is true. And vice versa, if the observation had been in the tail, then you would have answered that question as no, the observation is not consistent with the idea that HO is true. Any questions so far? So this next part, once you've decided on which of the two sides to be on, now we're ready to actually formulate the conclusion in words. And it turns out that from my experience, this is the part that trips students up the most often, is actually wording this conclusion. And the first time you see the wording, it seems like it's unnecessarily technical. It's filled with lots of words that might seem initially like they're extra words. But after we talk about it, there's a rationale for each of those words. And so if you understand the phrasing of the conclusion, then it will be straightforward. Otherwise, it will seem unnecessarily complicated. But before I just throw out what the conclusion is, let's build up to it. So we're going to start with, we're going to go back and talk about a simpler example, but remind you that this conclusion is in this particular context, which is We're answering the question of whether an observation is consistent with an idea. In this case, the idea just happens to be the idea that HO is true. But ultimately, all we're doing is answering a question about whether the observation is consistent with the idea. And if it is, then we phrase the conclusion one way, and if it's not, we phrase the conclusion another way. So let's use a much simpler, more absurd example. Let's say that your idea is that all sheep in the world are white. And for simplicity, I'll just say all sheep are white. And you know that means every single sheep. And to test the idea, let's say that you have an observation. And in your observation of 104 sheep, let's say all 104 are white. In this case, is the observation consistent with the idea?
Unfortunately, yes.
Okay, so good. In this case, the observation is consistent with the idea. So the question is, because this one observation of 104 sheep is consistent with your idea about all sheep, what can you do about accepting the idea? Can you just accept that the idea is true, that all sheep are actually white? Just because this one observation was consistent with your idea. Yeah, no, so you can't just accept your idea that all sheep are white. So you can't do that. So the best you can do is hold on to the idea, don't toss it out. Don't throw out your idea, but hold on to your idea, and maybe after you're able to observe all possible sheep in the future, then you can finally embrace your idea. But for now, the best you can do is not throw out your idea. So in words, we say, fail to reject the idea. But when we say fail to reject, that means hold on to the idea, don't reject the idea. When we say fail to reject, we don't mean that you can never reject the idea in the future. It just means for now, don't yet reject the idea. So another phrasing that's common that emphasizes that idea is there's not enough evidence to reject the idea. So you'll also see this as there's not enough evidence to reject the idea, or insufficient evidence. Any questions? So if you have an observation that is consistent with your idea, like you've observed these 104 sheep and all of them are white, you can't just accept your idea and say that all sheep in the world are actually white. The best you can do is not throw out your idea, fail to reject your idea. But fail to reject, and notice that fail to reject is not the same as accept. So they're completely different. Accept is you full on embrace the idea. Fail to reject means that you just can take any position as long as you're not rejecting the idea. Any questions so far? So this is a very weak conclusion, and another way to help you think about this is that we have the entire spectrum of possible conclusions. We have accept on one end and reject on the other. And you have this entire spectrum in the middle that you could take a position on as well. So when we say fail to reject, all we mean is that we're allowed to take any position here as long as it's not flat out rejecting. So flat out rejecting doesn't mean accepting, which is all the way on this other end. It just means that you can take any position in between as well. So another way that you can think about it is fail to reject doesn't mean accept, but maybe you're leaning towards accepting. So fail to reject doesn't mean full on accept, but you're leaning towards accepting. Okay. So that's the case where you have an observation that's consistent with the idea. Then the conclusion would be you fail to reject the idea. But let's say that you have the same idea, all sheep are white, but this time your observation is out of 104 sheep, you have only 101 that are white, and the rest are gray, let's say. In this case, is the observation consistent with the idea?
Rigging variables, are they dirty or are they just a gray coat?
Let's say that they're definitively a different color, like gray.
Well, no, that observation is not consistent. with
Yeah,
that.
so in this example, the observation is not consistent with the idea. So in that case, what conclusion do you think you can make regarding the idea that all sheep are white?
Reject it.
Okay, very good, because it's not possible that all sheep are white, because already there's these 3 sheep that are not white. So your idea that all sheep in the world are white can't possibly be true. And you can go ahead and reject outright this idea that all sheep are white. So you notice that this is actually a very strong conclusion, because you're able to reject the idea flatly. You're taking this position here that's all the way on the definitive side of the spectrum. So you have 2 possible cases. One, where if the observation is consistent with the observation, then you make this very weak conclusion, fail to reject the idea. But on the flip side, if the observation is not consistent with the idea, then you can go ahead and have a very strong conclusion of being able to reject the idea. So why is there this difference in the strength of the conclusions?
Because when you say you either accept or reject, you have an absolute, whereas definitive and proved by either a number of trials or data supports that the statement cannot be true based on the claim and the information provided. You have concrete facts that support the data. Whereas when you're giving that weak hypothesis in between it where you're saying it's either insufficient or you can't dismiss it at this time, it's because there's not enough data to actually prove that point definitively to say 100% rejected or accepted.
Okay, very good. So basically, when you're trying to show that an idea is true, and that indeed all sheep in the world are white, you can only show that an idea is true if you're able to show that it's true for all possible cases. You have to be able to observe all sheep in the world and have all those observations of all sheep in the world be consistent with your idea for you to be able to show your idea is true. So, to show that an idea is true, you have to prove it for all possible cases. But to show that an idea is false, you only need one counterexample. So it's much easier to show that an idea is false and disprove an idea than it is to prove that an idea is true. So that's why that in the previous case, when we had evidence supporting our idea, it was limited evidence. And we were not able to just flat out accept the idea, because we need to be able to show that all possible cases are true. But in the other case, in rejecting the idea, we only need one counterexample to show that it's false. Any questions? Okay, so that's for this example of this absurd idea that all sheep are white, and what you would do in the case where the observation supports the idea versus not supporting the idea. But now we know how to correctly phrase the conclusion. And one thing I want to emphasize is that if the observation is not consistent with the idea, the second case, then we can flat out reject the idea. And to emphasize that, that means that with just this observation you have, 104 sheep, we're able to make this strong conclusion and flat out reject the idea. So another way of saying that is that there's enough evidence already to reject the idea. So you'll see on your homework, it might say there is sufficient evidence to reject the idea. Versus over here, when you fail to reject the idea, there's not enough evidence to reject the idea. Okay. Any questions? All right, so now we're going to go back to the example we started out with the coin. So in this case, we're observing 55 heads after we flipped the coin 100 times. And in that case, this 55 heads was in the body of the distribution. Because it was in the body of the distribution, we said that the observation was consistent with the null hypothesis, with the idea that the coin is fair. So back to this case. The observation of 55 heads ended up being consistent with the idea that the null hypothesis was true, i.e. the coin was fair. So if the observation is consistent with the idea, what phrasing can you use on the conclusion? Can you just accept the idea that the null hypothesis is true? Based on what we just talked about. If the observation is consistent with the idea, can you accept the idea?
Not outright.
No, not outright. You can fail to reject the idea. Very good. So, in this case, your conclusion would be fail to reject the idea. And the idea under consideration in this case is that HO is true. So you would fail to reject HO. Vice versa, if the observation had been in the tail, i.e. 90 heads, then what conclusion would you make?
You get a z-score of 8, which is greater than 3.5, which is where you're going to say is definitely in the tail. No, HO is not true.
Yeah, so if the observation had been in the tail, then that means the observation was not consistent with the idea, just like with the sheep, and you'd be able to flat out reject the idea. So in this case, again, the idea is HO, so in this case you would, if the observation were in the tail, you would reject HO. Again, we see this difference between much stronger conclusion if the observation's in the tail. If the observation's in the body, then you have a weak conclusion. But these are both correct conclusions in terms of HO. Now we want to make also a correct conclusion, but in terms of H1. So, if we had said fail to reject HO, what do you think we can say about the opposite statement, which is H1?
Directly inverse.
Yeah, so it turns out that the opposite of fail to reject isn't accept, but it's going to be fail to accept. And again, fail to accept doesn't mean you reject, but you can think of it as leaning towards reject. And alternatively, if the observation had been the tail and you reject HO, what do you think you can say about H1?
Accept H1.
Very good, because there's only these two possible statements for this whole universe of possibilities for this coin, whether it's fair or unfair. So if you can reject HO saying that the coin is fair, then you must accept the alternative statement. So if you can reject HO, then you accept H1. And on this end of it, where the observation is in the tail, these are both very strong conclusions. Okay, so now on each side, you have two statements that are just as true, but one's in terms of HO and one's in terms of H1. So in hypothesis testing, you always want to bring it back to the original claim that you started out with. So here, the original claim was that the coin is unfair, but that claim is HO or H1, based on step 1 of hypothesis testing.
Identify the null and identify the.
Yeah, but was the claim HO or H1?
The claim is whether the coin was fair or not.
Well, the claim was outrightly that the coin is unfair. So based on what we did in step 1 of hypothesis testing, did we say that that claim was HO or H1? So we already labeled it in the picture, right? So claim is H1, good. So we always want to bring it back to the original claim. And in this case, the claim is H1. So then what we said, and then we go to what we said about H1, which is we said, because the observation was in the body, we're on this side, we said to fail to accept H1. So in this case, because the claim is H1, we fail to accept the claim. Any questions?
What are the wording on that?
Yeah. So the wording is very confusing. So again, when we say fail to accept the claim, again, we have the spectrum of all possible positions we can take. And fail to accept means that basically you're allowed to take any position as long as you don't take this position of accepting. We're failing to accept. So we're not going to accept, but that leaves out all these possibilities here. So you can flat out reject, and then you can take any position that's just short of flat out accepting. As long as you don't flat out accept. So another way to think about that is you're leaning towards rejecting. So when you say fail to accept the claim, you're saying you're leaning towards rejecting the claim. And intuitively, if you compare that to the answer we got before, if you flip 55 heads, basically we said that maybe the coin is fair. So we're leaning towards accepting that the coin is fair. That means we're leaning towards rejecting that the coin is unfair, which is exactly what we're saying here. So we're failing to accept the claim that the coin is unfair, or we're leaning towards rejecting the claim that the coin is unfair. You guys okay?
Absolutely. I mean, when I look at this accept and reject part, and then the difference between H1 and H0, I understand that they're going to be inverse depending on how you put it, but it really feels kind of like, you have your variable and the complement of, depending on which one you're trying to describe. As long as, when you put them together, you have an absolute, or you have somewhere in the middle, you're gonna be fine.
Yes.
And that's kind of how I'm trying to put it into something that we've used in class already. It's like you have the complement and the actual variable. So you either accept or reject it, figure out which one goes to where, or you're gonna be somewhere in the middle, and your statement needs to reflect it.
Okay, good. So to summarize what we did in step 3 here, basically we're answering the question of whether this observation, 55 heads in this case, is consistent with the idea that the null hypothesis is true. In this case, the null hypothesis represents the coin being fair. That was step 2, assuming the null hypothesis is true. So that was the coin is fair. So based on step 2, we decide whether the observation is in the body or the tail by comparing these two z-scores. And once we decide whether the observation is in the body, for example, then we go to the left side in green of conclusions. The observation is in the body. If the observation had been in the tail, like 90 heads observed, then that would be the right side of conclusions, or the red here. So if the observation is in the body, that means that the observation is consistent with this idea that HO is true. And so if we have an observation that is consistent with the idea, we said that that doesn't mean that you can accept the idea. But that means that you fail to reject the idea. And also that doesn't mean that you can never reject the idea. It just means that for now, we don't have enough evidence to be able to reject the idea. For now, don't reject the idea. So, the wording that you'll see on your homework is that there's insufficient evidence to reject the idea. So, that's the conclusion in terms of HO, because the idea under consideration now is HO. So when we say fail to reject the idea, we say, in this case, fail to reject HO. And then if you can fail to reject HO, now we're ready to make the conclusion in terms of the opposite statement, H1. So it turns out that the opposite of fail to reject is fail to accept. So if we say fail to reject HO, then equivalently, that's fail to accept H1. And again, fail to reject on top here doesn't mean accept, but you can think of it as leaning towards accepting. So fail to reject is leaning towards accepting, and fail to accept doesn't mean reject, but it's leaning towards rejecting. And again, once you have these two conclusions, you always want to bring it back to the original claim. And the original claim was that the coin is unfair, and it associated with H1. So now you go back and you look at what you said about H1, which is fail to accept H1, and because H1 is the claim here, we say fail to accept the claim. And the claim is that the coin is unfair, so we said fail to accept that the coin is unfair. And failing to accept is leaning towards rejecting, so we say we're leaning towards rejecting, the coin is unfair. Which is informally exactly what we said here, when we said maybe the coin is fair. I know this is all very confusing, especially the very first time you hear it.
It's no different than learning a weighted scale.
Okay. A weighted mean, you mean?
No, weighted scale, right? So you have your different scores of classes. Think of it like your algebra classes. Some of them have 3, 4, 1 credit, whatever, but then you add them all up with different parts, and because it's weighted differently, you end up with your grade.
Okay.
You know, variables change. You're using the same phrasing right there that they used to grade that score.
Okay. Everybody else okay?
So, we say fail to reject and fail to accept because we're working with a sample and not an entire population. I ask this because the homework gets tricky sometimes. And they ask
Yeah, no, this conclusion in the end will be towards the entire population. So you fail to reject, for example, HO, and HO has to do with the entire population of coin flips is fair. So all of these conclusions are population conclusions.
Okay, that does answer that. So it wouldn't necessarily change from fail to reject to accept if we had tested the entire population or an amount approaching infinity. It would always be fail to reject.
Right, so you're using a limited sample to make a conclusion about
Yeah. So that's
a large population.
That's what I'm saying is if we tested instead of the sample the entire population, like if the homework asked about the entire population, would that still?
So these would be the conclusions for the entire population. Okay. So we're almost out of time, but this is gonna take consistent practice. Basically, almost everything that we do now till the end of the semester will involve hypothesis testing. But if you understand this framework, this will apply to everything that we're gonna do moving forward. So if you understand this, then everything we do moving forward will be very straightforward. So one thing that I want to mention is that in step 2 here, when we decided whether the observation was in the body or the tail, by comparing two z-scores, the way that we calculated z-critical, where the tail starts, we used the chart. The way that we calculated z-test, we actually used the formula. So the formula we used was just the z-score formula. It turns out that the formula that we used in class will look a little bit different from the formula that's shown to you on the homework. The answer will be exactly the same, no matter which formula you use. But let me show you both, just so you're not confused on the homework. So in class, this is the formula we talked about. So it's basically the observation number of heads that we observed, like 55. Subtract out the mean, and then divide by the square root of NPQ. This is so this is actually the formula we used, and the numbers that corresponded to those variables was here. N is 100, P is 0.5. So that's the formula we talked about together. And the formula in the book is going to be this formula. So you'll see that at first glance they look different. But let's practice using the second formula as well. And then on your homework or test, you're free to use either one. You'll get exactly the same answer. So this formula in the book, the first variable is p hat. You guys remember what p hat represents? So the hat tells you that it's a sample variable. So this is the proportion of success, but in the sample. So in this case, what would that be? If you're observing 55 heads.
0.55.
Yeah, and so 55 is the number of heads you observed in the sample, but the proportion of heads in the sample will be 55 divided by the total in the sample, which is 100. So 55 divided by 100 is 0.55. So this p hat is 0.55. And compare the difference, we had used just the number of successes, 55, and the formula over here is using the proportion of successes, which is 0.55. And so, what would this p be without the hat?
0.5 or 1/2.
Very good. So this is the proportion of success in the entire population of coin flips. We don't know what that is, but we're assuming in step 2 of hypothesis testing that p equals 0.5. So that will be 0.5 here. And then down here, we're going to use p as 0.5 again, which means q is 0.5, and n will be 100. And if you plug in the second formula, you should see that you'll get exactly the same answer as before, which is 1.5. And it turns out that that's not a coincidence, that these two are the same. If you use a little bit of algebra, you'll be able to see that both formulas are the same. So basically over here, this is x, and over here, this is x over n. So basically, you're just dividing both the top and the bottom by n in both cases. Going from the first case to the second case. You're just dividing both the top and the bottom by n. And essentially, just multiply by 1 and not changing the value. So that's why they're the same. So you can use a little bit of algebra, divide both the top and the bottom of the first equation by n, and you'll get the second equation. But the point is that they're the same, and you're free to use either one. Any questions? And again, this is calculating z-test for your observation in order to later compare to z-critical to decide whether it's the observations in the body or the tail. All right, any questions, guys? All right, that's it for today. Have a good day.